Hello, everyone. My name is Yipen. I'm from Food and Agriculture Organization of the UN. Welcome to today, the second session of the GLOSOLAN Soil Spectroscopy webinar. And this is the second session of this year. As probably many of you already know, we regularly run soil spectroscopy webinar every year with the different topics. Today, I'm glad to invite our distinguished speaker and Dr. Asa Gholizadeh, if I pronounce correctly, I'm sorry, to give a talk about how to use this technology to detect or monitoring soil contamination. Because during the last couple of years, many colleagues in the community asked a question if soil spectroscopy is able to measure or monitoring soil contamination or soil heavy metal elements, etc. related questions. So I have reached out to the ASA and to ask if it's possible to have her in our platform to give talk regarding soil contamination. Because ASA has been working on this topic since many years, it's very well known in our community. So it's our great pleasure to have Asa today to share her experience and knowledge. But before our webinar starts, and I would like to introduce some preliminary information regarding this webinar. So this webinar will be run in a Zoom platform. The audience will not be able to turn on your microphone and camera, but please feel free to send your message through the chat. And please also feel free to raise your question in the QA session. Our panelist, Wahid, he will be willing to answer your question in the QA session. And if I will be moderating the webinar for the entire session, if I see any questions can be interested, bring to the discussion after Asa's presentation, and I will leave it to answer live. And later on, we will let Asa to answer your question on live. So without further ado, and I will give the floor to Asa. And then at last, I also apologize. I forgot to introduce Asa as associate professor from the Czech University of Life Science, Prague. So we also acknowledge the contribution from her institute. And thank you very much, Asa. This floor is yours.
Okay, thank you, Yi. Hello, everyone. I should first of all say thank you, Yi, for this opportunity, and then also I should say thank you to Wahid, who is my colleague here at the department, and he is on mining engineering expertise, his expertise on that. I asked him for his kind help. Today, as Yi mentioned, I decided to talk about spectral sensing for soil contamination. You know, about the other soil properties, chemical, physical, specifically on soil carbon. There has been a lot of work and very valuable works, but about contamination, still it's going on. And there are less works on that. So I decided to focus on this topic today. So the title for this webinar is Spectral Sensing for Soil Contamination from Ground to Space. The outlines of the presentation are about generally about soil degradation, soil degradation types and impacts, soil degradation analysis, alternative, which would be proximal and remote sensing, soil contamination, and then we will talk about some case studies to answer some questions. that later I will tell you about the questions and what we have done to reach the question answers. And then we will talk about soil degradation related to SDGs, perspectives, and finally, we will go for conclusions. Okay, let's start with a sad story, actually. Okay. So you saw that soil is dying, and one of the main reasons is soil degradation. Soil degradation is actually a composite term. It's not it doesn't have a single definition. And therefore, in general, we can define that it is this decreasing the soil physical, chemical, and biological condition. And all of this has been caused by improper use or poor management. This caused that the soil change for its worse. And of course, it declines the soil health. And FAO is a pioneer in defining soil degradation and led the global assessment of soil degradation initiative. This initiative categorized the soil degradation to three major types: chemical, biological, and physical, which the manifestation of soil degradation includes some soil erosion, soil contamination, salinization, deforestation, loss of soil, carbon, which all of them had negative impact on land use, water resources, climate, economy, and society. A map of global soil degradation, which has been provided prepared in 2019, shows that due to overgrazing, overcultivation, mining, and urbanization, and in general, because of the unsuitable land use and inappropriate land management, the areas which covered with degraded and very degraded soil are very significant in all around the world. Therefore, an urgent soil degradation assessment and consideration is needed. As all of you know, that conventional soil assessment in general and in particular soil degradation is based on field investigation. It is discontinuous, it's slow and expensive. And also repeated acquisition of soil information are complicated, especially on a large scale. Therefore, rapid and effective assessment of soil degradation is very necessary for timely prevention and remediation. Some alternatives are available that we focus on proximal and remote sensing. Generally, due to nature of these webinars and the people who attend these webinars, for sure you know that spectral sensing is the acquisition of spectral information from objects. And using proximal and remote sensing with a spectrum that obtained from them, the chemical composition and its texture within the field of view of that specific sensor that we use can be obtained. In addition, with recent advances in Earth observation technologies, proximal and remotely sensed imagery with high spatial, temporal, and spectral resolution is more accessible than before. From all the soil degradation, different kind of soil degradation factors, we focus here on soil contamination. Actually, soil contamination is a typical soil degradation phenomenon which caused by presence of some chemicals such as pesticides, fertilizers, some petroleum hydrocarbons, and the heavy metals and potentially toxic elements in the natural soil environment. Because of the difficult decomposition and easy accumulation of these particles, the problem of heavy metals and PTEs pollution in soil is one of the most prominent. Heavy metals ions exist in discrete energy state, and the electron move in specific energy level orbitals, which results in electron transition from low energy in the orbitals to high energy d orbitals. This transition leads to the absorption of spectral characteristics of heavy metals, which can be observed in visible and near-infrared range of the spectrum. Regarding to assessment of heavy metals and potentially toxic elements that we mostly focus on these contaminants in this webinar, we should say that the direct spectral sensing of them is a bit challenging due to their weak spectral signature, and it's only effective when we apply in contaminated soil with very high heavy metals and potentially toxic element pollution levels. However, if the heavy metal levels are low, they are usually determined indirectly using their correlation with some spectrally active soil parameters, such as soil carbon, clay, or iron, or we can indirectly assess them with based on their effect on vegetation as their proxy. Here you can see in this figure that mostly sensitive bands to heavy metals and potentially toxic elements are in visible and infrared range. Soil contamination affect the soil status, and therefore affect to soil's reflected and radiated signals, which can be detected by proximal and remote sensors. Actually, we can say that using different data sources, such as visible near-infrared spectroscopy or multispectral, hyperspectral, or superspectral remote sensors, we can use those data, and then using some approaches, algorithms and approaches and mathematical models, the soil degradation can be assessed quantitatively or qualitatively. And this can be used later for some applications such as temporal changes, spatial variation, mechanism of the pollution, and so on. In general, the extraction of soil contamination information is a process based on proximal and remote sensing images or data in general, spectra, and mathematical models. So using this, we decided to, with this information, we decided to answer some question that has been arose. One of the questions was, is reflectance spectroscopy feasible to estimate potentially toxic elements in anthropogenic soils of brown coal mining dump sites? For this, we had a case study. I called it case study 1, which was conducted in Czech Republic using proximal sensing. 206 soil samples collected from 4 different dump sites, mostly in northern part of the country, and some potentially toxic elements content measured. Then a spectral measurements was conducted using AST field spectry, and we did some spectral pre-processing, and finally we developed models. Actually, I'm not going through the detail of the methodology as I has been asked to do so, and just we are going to some general methods, and I just show you the plan of the study and some results. Based on the result that we had here, you could see that to visualize the spectral implication of potentially toxic elements, some correlograms were plotted. Linear correlation coefficient between reflectance and potentially toxic elements were low to moderate, although it was indicated that potentially toxic elements contribute to the reflectance of almost all wavelengths. The applied approaches provided the good performance of the potentially toxic element models. You can see here that we had, for example, copper, magnesium, iron, cadmium, lead, zinc, and arsenic. And we run two machine learning models. And finally, we modeled the PTEs. And these approaches provided good performance of these PTs, particularly the SVMR technique. In another case study, again in Czech Republic, we used proximal soil sensing to respond the second question, which was, can reflectance spectroscopy and learning algorithms assess PTEs in forested areas at a national scale? To answer this question, this study actually explored the potential of the combined use of soil visible near-infrared spectroscopy and some learning algorithms, including some approaches of machine learning and one deep learning approach in organic horizons of the Czech Republic's forested sites to model soil selected PTEs at the national scale of the country. Here you can see that we collected about actually almost all the country, all the forested site, which is about 34% of the country. Czech Republic has been covered by forest, about 34% of the area of the country. We collected about 2,160 soil samples from two different organic horizons of the soil. And the soil were taken to the laboratory to measure their heavy metals, including chromium, copper, lead, zinc, and aluminum, and also soil organic carbon as a spectrally active soil parameter. The spectral measurement, again, was done using AST field spectry, and spectral pre-processing was done as usual, and model development was conducted using 3 machine learning algorithms and 1 deep learning approach. Here you can see that for visual inspection of the spectra, inspection of the spectra in different horizons, which was one horizon F, fermented, and one horizon H, humus. And in another one, we merged the sample, the data from both horizons, which we called it horizon F plus H. Visual inspection of the spectra indicated that the overall reflectance patterns and waveforms of the spectral curves of different horizons were roughly the same. The horizon F, fermented horizon, had higher reflectance values compared to the other one, H, and also compared to combined horizons. Then the correlation between attributes and measure reflectance for each wavelength showed that Potentially toxic elements contribute to the reflectance of almost all wavelengths in the visible and near infrared range. The concentration of PTEs in the F and F plus H horizon showed correlation in a wider range, starting from 0.5 to 0.4. And it was throughout the spectral region, as they were correlated via their high content of organic matter. This can be, as I told, it can be due to higher content of organic matter in layer F and F plus H. So maybe this could be the reason for this higher correlation. And the correlation also, correlogram also illustrates that all potentially toxic elements in both horizons displayed their maximum correlation in the visible range around 430 to 450 nanometer, and their highest negative correlation, it was in near infrared range, somewhere between 1040 to 2,300 nanometers. After development of the models using three machine learning algorithm, PLSR, SVMR, and random forest, and fully connected neural network deep learning approach, we got that in general, chromium and aluminum were the best predicted elements, whether they were based on machine learning or deep learning models. This was expected, actually, based on the strong positive correlation coefficients that these heavy metals have with visible and near infrared spectra. Then we found out that among machine learning approaches, the best prediction is nearly in all cases, regardless of the soil element, was achieved using SVMR. However, applying the deep learning approach, fully connected neural network, the best prediction performance seen for the combined horizon. It means that when we had the soil samples of both horizons together, FNN provided us the better model. And this was also, I guess it was expected, because it can be related to the bigger sample size, which is the nature of the, actually the need of the deep learning approaches. Then we had three other more case studies called case studies 3 to 5, which were conducted in Iran using proximal and remote sensing. As the study area and the general methodology of these studies were similar, I show all part in here in one slide. This study, the study area was called Sarcheshme copper mines, which is about 160 kilometer. You can see here in the middle part in one of the province called Kerman. It's the biggest copper mine in Iran and one of the largest in world. Due to mining activities, over 400 million tons of mining waste have been produced and dumped in natural valleys at the vicinity of the mine, and resulting in 31 active and inactive waste dumps, some of which generate acid mine drainage. So we chose this area as our study area. 120 soil samples were collected from one of the waste dumps. Measurement of toxic elements content plus pH, organic matter, clay, and Fe, iron, was conducted. And a spectral measurement using AST field spect was with AST field spectry. Common spectral preprocessing techniques were done, and we also provided some satellite data, including Aster, Hyperion, Sentinel-2A, and also Landsat 8, which in this table, you can see the specification of each image that we used for these studies. Okay, first we decided to use proximal sensing to answer the question, the next question, which was further to quantification of content. Can reflectance spectroscopy determine the speciation of cobalt and nickel on a mine waste dump surface? Actually, toxic elements released due to mining activities are of the most important environmental concern, characterized not only by their concentration, but also by distribution among different chemical species, that it's known as speciation. This study mainly aimed to explore the possibility of using visible near-infrared spectroscopy as a tool for assessment and determination of the cobalt and the nickel speciation. Okay, so as you can see, I told about data collection, 100 soil samples, and then, as I mentioned, some pre-processing and the modeling and analysis were conducted. We used some pre-processing of the spectra, and then we used support vector machine, random forest, and also extreme gradient boosting to predict, actually to develop the predictive models. Then cobalt and nickel distribution maps were created, and the maps provided map compared with the observed map which was produced based on the laboratory data. And finally, a spectroscopic based of cobalt and nickel speciation was conducted, which was compared with a previous study, which assessed this speciation using some conventional methods. I don't know why it doesn't show the slide here. Can you see the maps? Because the maps...
No, it doesn't show. It shows just 1 second and disappears.
Yes, same for me.
Maybe can you go back to the to not the presentation mode and come back again?
Just let me see how to do. Maybe I need to stop sharing once. A moment, please. Can you see that?
Who was sharing just now?
I'm sharing, but unfortunately it disappears. It doesn't show. So let me try once more.
I think I can show the map from.
Ah,
No,
no? Maybe you can
no.
show it. Can you try it on your PDF that you have?
Yeah, if you can stop sharing. Right?
Yes, that's true. Okay, the study showed that the extreme gradient boosting technique was very successful in indirect quantification and spatial variability mapping of cobalt and nickel on the mine waste dump. And also the spatial variability maps of elements showed relatively similar patterns between the observed and the predicted values. You can see here that spatial distribution map of A and C are the observed for cobalt and nickel, and B and D are predicted by visible near infrared spectroscopy. So do you think we should continue like that, or I need to?
You can try with yours. I think maybe it's
Okay.
better. Otherwise, we can do it again.
Okay. Mm-hmm. No. What about here? I'm sorry, but I don't know what's going on. Maybe I don't know why it doesn't show some of the slides. Okay. For speciation studies, we conducted two Pearson regression analyses to investigate the correlation between just the first nickel and cobalt with other soil parameters such as clay minerals and iron oxide, and then nickel and cobalt and spectrally active and spectral response of the soil samples. For the first one, you can see on the first table, and you can see that regarding this correlation with other soil parameters, a relatively high positive correlation was observed between cobalt and nickel, and also a moderate correlation was seen between clay minerals and iron oxides. And both toxic elements showed higher correlation values with iron oxides than clay minerals. Then regarding the correlation with the spectral information, you can see that most of correlation of the two toxic elements with the spectra was relatively similar at a similar wavelength. For both examined heavy metals, visible range provided the maximum correlation, which is associated to the iron oxide and the hydroxide, indicating that the higher importance of these soil parameters in prediction of cobalt and nickel. However, the relatively high correlation coefficient in the shortwave infrared region also shows the importance of the clay minerals. You can see that the correlation have been reported between clay minerals and soil chromium and cobalt. Considering you can see that the actually affinity of the toxic elements with iron oxides and clay minerals to lesser extent can be important factors affecting their speciation. So the study answered the question that visible near infrared not only can quantify these soil heavy metals, cobalt and nickel, but it could help for these parameters speciation. Then we go for the next question. Maybe, should I continue like that, or should I try once more? Okay, sorry everyone for this inconvenience. I do not know what's going on with that. Okay, I think you should see that. Okay, the next question was about the remote sensing of using remote sensing data for monitoring and mapping some heavy metals. Actually, we wanted to answer that: can satellite imagery efficiently monitor and map soil chromium pollution in mine-based dumps? The main objective of this study actually was prediction and mapping of chromium in the copper mine that we talked about, using some images from different satellites, and the capability of Hyperion, Sentinel-2 and Sentinel-2 in chromium prediction and mapping, compared with the performance of Aster and Landsat 8. You can see the study plan here. In this study, actually, to predict chromium concentration in 120 soil samples, which collected from one of the dump sites. The samples, mineralogy and chromium concentration were assessed and then subjected to laboratory reflectance. The raw spectra were pre-processed using the common Savitsky-Golian first derivative and also the second derivative. And the importance wavelengths were determined using PLSR and genetic algorithm. Then artificial neural network, SMLR and PLSR data mining techniques were applied to on the selected spectral variables, which were selected using the techniques that I mentioned. Finally, the developed models were then applied to the selected bands of Aster, Hyperion, Sentinel-2, and Landsat satellite images of the area. Here you can see that the chromium concentration ranged somewhere between value of 3 and 137 milligram per kilogram, and with the mean of about 36 milligram per kilogram, which is very high considering the WHO recommendation safe limits. And then you can see that according to the outputs of the laboratory reflectance spectroscopy, on the left side, you can see the spatial distribution of chromium, which was measured in lab. And on the right side, you can see the predicted one. According to the laboratory reflectance spectroscopy, the highest prediction accuracy was obtained using ANN, which was applied to second derivative preprocessed spectra. It also, you can see based on the map provided based on that, you can see it's an acceptable performance of mapping of the spatial distribution of chromium using the ordinary kriging technique. A similar spatial trend you can see in these two maps. However, there were slightly difference in the chromium intensity of very high and low risk areas. Highly polluted areas located in the central and western part of the waste dump, which needs remediation plans for sure. And in opposite, very low concentration of chromium was detected in the north part of the study area, which both of them actually could be observed in both maps, measured and predicted. Then using satellite images, the model which provided the best prediction based on laboratory data was applied to Hyperion and Sentinel-2, and the model of the chromium was provided. This led to the higher visual similarity of the segmented Hyperion and Sentinel-2 image with the chromium distribution map. Accordingly, segmented Hyperion raster showed the highest similarity to the chromium distribution map, which could be explained by the continuous coverage of visible near-infrared and shortwave infrared region. The other reason also could be that Hyperion had the most significant number of similar wave bands with the sample spectra, 11 wave bands, compared to the other sensors. And in another study to answer this question, does integration of Sentinel-2 and Landsat-8 images affect the soil toxic elements model performance? We aim to explore the potential of individual images of Landsat and Sentinel-2, as well as their integration on quantity of some selected potentially toxic elements. For the fusion purpose, different fusion techniques were tested. And the study also employed genetic algorithm to select important wavelengths of the lab spectra needed for developing the prediction model to assess the impact of variable selection of performance on the final model. The study plan shows here, as has been shown again, and I should mention that the 30-meter spatial resolution Landsat-8 bands were integrated with the 10-meter Sentinel-2 bands using various fusion techniques. And the fusion techniques have been shown in another, I think I didn't browse the details of them. 8 different fusion techniques were used, and finally, we got that the best toxic element prediction performance was obtained by applying the PLSR model developed on lab spectra on the bands of the area to point regression kriging, or ATPRK fusion product based on the fuse imagery of the Sentinel and Landsat-8. And due to the selection of greater importance wavelength, the toxic elements estimation was better when we use the GA, genetic algorithm on PLSR. Here you can see the performance of these models using Sentinel and Landsat data individually, and then combined and integrated the image. Can see that except for arsenic, individual Sentinel-2A provided more robust prediction models than Landsat-8, although the fused product preserve both spectral and spatial features of both individual images of Landsat and Sentinel-2, and provided the best prediction models. So it means in general, first the fused, the integrated product, then Sentinel-2, and then Landsat performed well. Okay, so now we go to the soil degradation related SDGs. As all of you know, in September 2015, the United Nations Summit on Sustainable Development established the global agenda for sustainable development until 2030. And they actually defined a list of objectives on which to focus commitment for the next 15 years. These objectives have been, as you know, defined as Sustainable Development Goals, or SDGs, and economic development, pleasant environment, harmonious society, and their main sustainability aspects are among them. We explored all the SDGs, and we got that some of them are related to soil degradation. Actually, among 17, we got that the achievement of SDG 1, 2, 3, 6, 11, 12, 13, and 15 is directly related to soil health and soil degradation, consequently. For this reason, can say that soil monitoring is becoming a critical asset to understand the process leading to the loss of crop productivity, water pollution, and the loss of biodiversity, and soil pollution, among the others. In this regard, proximal and remote sensing technology is becoming important for soil degradation assessment, as the Earth observation provides reliable, updated, and cost-effective data sources, which can be applied to monitor the SDG-related parameters from a regional to a global scale. These SDGs cannot be separated from monitoring soil degradation. In addition, this remote sensing provide potential indicators, and the SDG concept uses these indicators. We can say that in general, this proximal and remote sensing, and we can say spectral information and data play an essential role in tracking of progress on SDGs implementation. So the perspective regarding to what mentioned here are to employ the emerging sensing technologies, big data and cloud computing. Actually, we can say that consequently it's necessary to take full advantage of information potential of remote sensing, big data, and cloud computing for multi-scale, multi-source, and multi-platform analysis of soil degradation and contamination. Here we mean focus on contamination to understand it better. Also, it's suggested to establish a continuous and harmonized soil monitoring system and decision support tools at a global scale to provide comparable data sets and chart the spatial extent and temporal changes in soil contamination, as well as corresponding economic implications. And also can say that assessing the spatio-temporal distribution of soil degradation using spectral data is only, actually is the first step, protecting local ecology and environment and ensuring the no expectation of soil contamination, no expansion of the soil contamination and degradation. It can be used to avoid its expansion, and then achieving ecological recovery and contributing to global sustainable development in our, actually as one of the ultimate goals. In general, in conclusion, based on mentioned and based on the case studies that we had in about this topic, regarding the proximal sensing, we could see that potentially toxic elements contributed to the reflectance of almost all wavelengths in the visible near-infrared range. We also got that the visible near-infrared range reflectance spectroscopy combined with machine learning approaches had great potential for site-specific soil monitoring in high-risk regions. Also, deep learning coupled with spectral data indicated the good visibility of modeling potentially toxic element based on the national spectral data of forested soil horizon in the Czech Republic. Also, visible near-infrared reflectance spectroscopy had the potential for speciation studies of soil toxic elements. The question that our studies answer regarding to remote sensing concluded that Hyperion and Sentinel-2 images could quantify and map chromium polluted soils of the mining area. Also, it got that the Sentinel-2 provided more robust and promising prediction models of heavy metals than Landsat 8. Although when we combined and integrated of both sensors images, it could enhance the performance of the prediction models. And finally, we concluded that spectral and remotely sensed data can provide independent insight and supporting evidence for decision-making and fulfillment of the soil-related SDGs of the SDGs. So thank you so much again, Yi, Wahid, for your support and all the audiences who attended.
Thank you, Alpha, for the great talk. And it's quite a lot of intensive work, and from Czech Republic to Iran. So your research covers the half of the world. And I forgot to mention to everyone, Asa is originally from Iran, and now she's working in Czech Republic. And during your presentation, and he was busy to help with the questions and spreading with some messages in the chat and distributing some paper in the chat. And I also just realized that I think it's because, apologies to the audience, because I think it's because our Zoom setting and couldn't allow the audience to really actually write a message in the chat. And afterwards we will go back to check it, because the previous webinar I already realized a little bit strange why colleagues in the chat are not writing a message, and I just really get the response from Cecilia, so that it's disabled this option. Besides of that, we have some questions from audience, and I would like to discuss with Asa. I think the first question is from Cecilia. I think it's an interesting question. And she asked that first of all, she thanks your talk. She asked that during your work, did you observe a minimum threshold of the toxic elements below which they cannot be detected by the spectroscopy? In a word, do we need a minimum level of the contamination to detect? If yes, what is the minimum contamination level?
Okay, Cecile, thank you for the question. You know, it's important, and it seems very, you know, it's one of the questions came to everybody's mind. You know, it's what is the minimum level? You know, most of the time, minimum level has been defined by WHO, and in Czech Republic also, as I know, some minimum levels have been defined. During our work, yes, we faced some issues regarding to low level of, it was about arsenic, one of the potentially toxic elements, and we couldn't assess that using this spectral data. But as I mentioned that when the low level of the contaminants are available, mostly it would be very difficult to, and it's very challenging to use a spectral data to receive the models and to quantify them, because these heavy metals and generally potential toxic elements, they have very weak spectral features, you know, and because of that, they cannot be detected easily when they are in low content. That's why we mostly use some correlation with some spectrally active parameters, such as iron oxide, such as clay, and such as soil organic carbon. This is one of the ways that you can detect them when they are in a low level. And the other way that we have not done it yet, but we have started in a project, it's their detection using their impact and their impact actually on vegetation. No, vegetation tolerance to heavy metals is much lower than soil. And you can use this vegetation as the proxy of the soil. And then using this vegetation indirectly, you can predict and assess that the soil heavy metal or whatever contaminant it is. Because in vegetation, even the level of the contaminant and heavy metal is low, they show some symptoms. And based on those symptoms and remote sensing of vegetation, and you can go indirectly to soil. But if I want to tell about what limits, I really do not know about the exact number. So it depends from, I guess maybe depends from, maybe depends from country to country, maybe policies, I don't know, or maybe it depends from the, for sure, depends on the kind of heavy metal. But if any discussion or if any comment, if something, I really welcome everybody who wants to join in this discussion.
Yeah, thanks. This is, I think this is going to be a continued discussion for the future as well, until we find really the answer, or also a universe level for the all the country. I think there is another simple question. I guess what he already addressed by the typing, but I think it's also good to address it here so everybody will be able to understand. Because one colleague, I think is Chinese, in Jianxin, asked, what about the MIR range? I think that's something, because I think that is more in the laboratory. It's not really possible to bring it to the proximal and the remote platform. Maybe you can elaborate a little bit more.
Okay, I cannot see the question.
No, he just asked, what about using the MIR range of the spectral application for the detecting the heavy metal in this kind of question?
Actually, I have not seen that. I have not used that. And also, as it has been mentioned, especially during in 2000, this new year, 2024, there is a very, very good review paper about the remote sensing of soil contamination. They have also emphasized that the best range, the best region are, of course, after X-ray. You know, you can, because XRF is one of the best, using XRF sensors, one of the best for heavy metals. But in compared to visible near infrared and this mid infrared, however, mid infrared has not been reported yet, but they have emphasized that especially visible would provide very promising results, and then an IR. But we actually at our team, in our department, we have never used MIR. However, if I can have the opportunity, if I have the data, of course, I will go through that to see the result.
Yeah, thanks. And also, I think also when we talk about the mapping, especially in a large area, for the MIR, it's not possible to provide the larger the covariance, the raster file like images, because that range of the spectra is not going to the space or the remote platform. That limited something from a mapping perspective.
Yes, for remote sensing, it would be, maybe for proximal finally works, but for remote sensing, it would be a big challenge. It's a big limitation.
Yeah. I think there is a question is, I think many people ask the same similar question. Do you think, yeah, what he just answered, but I think it's also to address it here, because he just addressed this question and then suddenly disappeared. Is do you think having the R square around 0.5 is enough? Or do you think the analytical approach should be improved until the application become ready? So it's difficult to discuss. It's difficult to answer it's ready or not ready. So please feel free to share your opinion, Asa.
It's the question, as you told, it's frequently asked, and you mean about the R square, yes?
Yeah.
This is not, you cannot say that, it's a very difficult question to answer. What, which range of R square is good? Which range of the R square is reliable? I guess, you cannot extend it. For example, if 0.5 is good somewhere, you cannot extend it to other areas or other parameters, or it's not something that, and it's not only accuracy, with this you have the accuracy. So what about uncertainty? Maybe sometimes you have 0.8 R square, and then at the same time, you have the high RMSE and high bias. So it's not something that you can rely on in this 0.8 R square. I think this is a question that should be, I don't know, discussed a lot, and I think it will never be answered very properly.
Yeah, I think one of the main issue here is most of the people relies on R square too much. I don't think we should only look at R square, and also to think about the what is our the objective of our application as well, which come to the next question. Cecile posed one question, and she asked, don't you think that predicting classes of the toxic elements instead of the quantitative value would be enough for the stakeholder? So we classify the levels, basically high, low, very low, medium, yeah, something like that.
It depends on the classification. If we say high, low, medium, maybe, it's not very actually precise, but if there is no opportunity actually to have the quantification, to have the quantity and content, okay, it would be still okay. It's better than not having any information about it. But in general, it depends how many classes you have. Is it only high and low, or is it but I know that at least in the Czech Republic, there are in some areas, in some mining areas, they work with these classes only, not with specifically the quantification, with the content and concentration. There are some areas yet that they work with that. So it means it works for them. But of course, quantification would be much desirable.
Yes, but I don't know if actually it's possible to we can think to write something to propose about to propose a kind of the classes, at least to start have this concept in a community for the people to consider. But anyway, well, there is a very general question. I can speak a little bit, but Asa also maybe you also can speak a little bit on behalf of the community, because one colleague asked, is there any chance to study workshop or something for learning a protocol or method by the FAO or university? So I can speak a little bit from the FAO side. From the FAO in the GLOSOLAN Spec, it's an initiative initiated by the Global Soil Laboratory Network, and one of our objectives is to strengthen the national capacity. So we try to develop some workshop or regional, national level to invite experts to give some training. For example, in April, we have organized a Latin American regional workshop, invited the laboratory within the network to join, which is completely free. So we had 3 days of the training, 2 days focused on wet chemistry, 1 day focused on spectroscopy. I know 1 day training is it's not enough, but we're starting. So if you would like to have some information about the training or workshop, training program or workshop within the FAO or GLOSOLAN framework, please feel free to register in the GLOSOLAN network, and then you will be able to receive all this training information, upcoming training information. For example, we are currently preparing a workshop this year, maybe after summer, for the Asia region, possibly in Philippines, if I remember correctly. So please feel free to get into the network, and we will distribute the information, and we will try our best to mobilize more resources and fundings to organize such activities, and also invite the experts within the network to share their knowledge with different opportunities. So Asa, if you have any information to share with everybody from your university or from a community, please.
Now, regarding to this, I don't know about I think Mr. Manucher is talking in general or talking about this contamination. But in general, time to time, we have some workshop, but it's not very, it's not something usual and frequent that we can announce. Or, for example, last week we had a workshop on Friday. We had a workshop here at our university about the soil organic carbon, actually about MRV, monitoring, reporting, and verification, based on for the soil organic carbon and some climate, greenhouse gases and climate change. But it's for the contamination, we had about 5 years ago, and since then we didn't have any. But if we know some people, especially for the contamination, I know not only myself, I work on the spectral part of that, but there are some colleagues here that they work on the soil contamination specifically on soil science. They are soil scientists. And time to time they have something, but it's not something that we know from, for example, in advance about some months. But if there are something and there's something and we know some people are interested, especially in contamination, I can say that our department works very well and hard. So we can inform people if we know some people are interested in.
Thanks, Asa. But I think Asa speaking about this, if your university or your institute is organizing something related to the laboratory analysis or spectroscopy, I think please feel free to share the information with us, and then we can try to distribute or also put in our website, and many people will know.
Oh, sure. I didn't know about it really, because if so, last week on Friday we had, and it was difficult for us to, and we mostly were thinking about some stakeholders in addition to researchers. And I didn't know that it's possible from your channel. Okay, good to know.
We have it even. Yeah, it's good. And another question is about the XRLF. Ask if you have any experience about this, and would like to ask you to share any of your insight about using XRLF.
About XRF, for sure, we did it, I think, in 2022 or 2021. We published one with this using XRF. Then we compared that with visible near infrared range, and then we integrated both ranges together, XRF plus visible near infrared. And it was not surprisingly, but we saw that, of course, XRF provided better results. And when we combine and integrated that XRF range with visible and near infrared, there was not any significant, it was not that much, not significant improvement. And of course, XRF provided good results. We have one paper about it, we published that, so I need to find and share it.
Okay, in the meantime, I will check there is a last question in QA. If there will be time for one more question. Heavy metal may be found as some oxidates or hydroxidates or complexed with organic matter and exchanged in clay, respectively. Their environmental dates and the danger are different. Do you detect them separately, or there is a cumulative estimation of heavy metals? Wow. I don't know if you can see this
I can
question.
see that. Yes,
Yeah.
I can see that. I'm trying to understand it. Do you detect them separately? If you mean by detect them, you mean the heavy metals. As I told, we have in our studies we did this assessment sometimes directly. Very directly we assessed and detect this heavy metals. And sometimes we, in some of these studies, I think the studies that I showed today during this webinar, I think 3 of them, most of them actually used the correlation between these heavy metals, these contaminants with, as you told, organic matter and iron or clays. So it depends on the level of contamination. We both use both assessment directly or heavy metals, or when they are combined and bond with spectrally active parameters. If I could understand the question well, I hope I could provide the result, the answer.
I think that I saw this question, and also I think also because of the spectroscopy it's not a direct measurement. It's something we need. We need the wet chemistry data associated with the spectral data to build a calibration model as an empirical approach to estimate the unknown sample. So if we are able to measure the heavy metal is it's oxidated or not, I think it's also depending on the reference data is coming from what type of the wet chemistry data. It's not so straightforward or direct, I think, also. Of course, if we have a different type of the wet chemistry as a reference data, I think probably we can try. Yeah. Okay, I think we have completed all the questions from QA. I don't know if colleagues still have any other questions, but if you have any other questions which is related to using soil spectroscopy for the soil contamination, please also feel free to reach me or reach the Asa or Wahid from Czech University of the Life Science in Prague. I think the Wahid, if you can share the webpage of your research group in the chat, so the colleagues will be able to find the contact information of your research group, Asa and you, and maybe one day some of the colleagues will reach you for the different purpose collaboration or maybe go into your institute for the study, because the first question was asked if there is any PhD position in your institute. Yeah, this is Also, the Asa is working as a social professor in the university, and she's supervising PhD students and postdoc. And if there is any opportunity, I think the information will be online as well. So colleagues, if you are looking for the opportunity, come to the Czech Republic for the PhD or the postdoc, please also regularly check the information in their website. Okay, thanks again, Asa, for a great talk and also the interesting discussion. I think our webinar will be closed today now. And thank you everyone for participating in today's webinar. And please also following our website, and the video recording and presentation will be uploaded soon, normally within 1 week. And you will be able to watch the video recording and download the presentation. Please also feel free to share the video recordings to them within your network, because I know it's always a problem for us to decide the time. In some of the regions too late, some of the regions too early, so colleagues won't be able to join the live session, and so they will be able to watch the recordings. And we will also organize the next webinar in June. So please also feel free to share the next webinar information with your network and follow our website. Thank you very much, and have a great day. Bye-bye.
Thank you, everyone. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.